turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
Discoveries.
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists, the programme that brings you the latest breakthroughs in science, technology and medicine with me, Chris Smith. It's another instalment of Titans of Science this week, and today is the turn of another out-of-this-world guest, Cambridge University's Astronomer Royal, astrophysicist, cosmologist and science populariser, Martin Rees. Martin Rees was born in the city of York on the 23rd of June 1942. He's a world-renowned cosmologist, astrophysicist and science communicator, and he also served as the Master of Trinity College, Cambridge from 2004 through till 2012. Martin grew up in a rural area of Shropshire, near the border with Wales. His parents, who were both teachers, founded Bedston College, which Martin would later attend, and he also studied at Shrewsbury School before reading mathematics here in Cambridge. On graduating from Trinity College with a first-class honours degree, he undertook postgraduate research in the Big Bang Theory at Cambridge under the tutelage of Dennis Sharma, who also taught Stephen Hawking, another notable name. Martin Rees has spent most of his working life in Cambridge, but he's also studied in Sussex, London and the United States. He was knighted in 1992, he was named Astronomer Royal in 1995 and served as President of the Royal Society as well. Martin is passionate about politics and he sits as Lord Rees of Ludlow in the House of Lords. He's a lifelong supporter of the Labour Party but has no party affiliation when he's sitting in the unelected upper chamber. You're a very special person for many reasons, but also because when we started The Naked Scientists back about a quarter of a century ago, you were the first guest on that programme.
Really, and you were very young then.
Do I still look young?
Yes.
Let's talk about the young you, though. I've said you grew up in Shropshire. Tell us about the young Martin Rees.
Well, I was very lucky because I grew up in this village in the South Shropshire Hills, beautiful natural world. My parents were teachers, and then I was sent away to boarding school, which wasn't quite so happy when I was 13. But I was very well taught, and I did get into Cambridge, and I read mathematics. I wish actually I'd done a broader curriculum at university, because when I got to university, I realised I wasn't quite the same as other geeky people doing mathematics, in that I like to think in a more sort of synthetic or synoptic way. I became a research student in 1964, and that's when quasars had just been discovered, the evidence for the Big Bang from the radiation, the so-called afterglow of creation, and lots of other exciting things, and theoretical work by Hawking and Penrose on black holes was being done. And advice I would still give to any young person starting is, if you pick a subject, pick something where new things are happening. And then the experience of the old guys is at a heavy discount, and you can immediately make an impact. So don't go into some sterile subject, because then you'll be trying to do the problems the old guys got stuck on.
Do you think then you got lucky with the subject? Did you have some foresight? Because you've said to me, go and pick something that's an exciting, emerging, evolving area that's current. Don't get stuck on the old stuff. Did it find you, or did you already have that view and therefore you were seeking out that kind of thing and you were able to say, well, I'm good at maths, I've got the kind of mind that would suit this, that's where I'm headed?
It was really just luck rather than careful planning. I had decided I didn't really want to pursue mathematics as a career. I liked the idea of something academic. I thought quite seriously about economics, because I had some good friends who had defected from maths to economics and did very well as economists, and I might have tried to follow that route, and I might have been happy if I'd done that too. But I was very lucky to get a place as a graduate student in Dennis Sharma's group, and it was luck, because it was because some other person who'd got the job in preference to me dropped out, and so I just managed to get my position as a graduate student.
So what was it about what was going on in Dennis Sharma's domain that really drew you in, and what did you think were the areas that were going to be the exciting ones to pursue?
Well, I realised that I liked a style of thinking where you try to make sense of something from limited information, rather than doing complicated deductive reasoning, like in mathematics. It was trying to make sense, a bit like engineering, where you try to make something that works from given specifications. And so we had these objects that were very bright, flashing away, and all that, which we now think of massive black holes in the sense of galaxies, which are called quasars. And I wrote some papers trying to understand that sort of thing, and also to understand the expanding universe, where the idea of an evolving universe was a fairly new one. And so I think it was a style of thinking that I quite enjoyed. I mentioned Dennis Sharma. He was very plugged into what was going on in all these fields, and he'd come in excitedly every day with some new preprint for the new paper he'd been sent and circulated. As I say, I was one of a number of students who he had. I mean, he had students like Stephen Hawking, who was 2 years ahead of me, and he told those students to go and listen to Roger Penrose in London, who had exciting new ideas, and they duly did, and followed them up spectacularly. He was someone who exemplified that you can be a great coach without being a great player. Didn't do any amazing science himself, but he was an enthusiast, and he inspired us all, a whole group in Cambridge, and then he moved to Oxford in the 1970s, where again he had an equally strong stable of students there.
Can you give us a sort of flavour for how the space science domain has evolved over the course of the time when you finish your PhD to where we are today? What have been the really big changes, and what have been the waves that you've most enjoyed surfing?
Well, of course, space science only really got started in the 1960s, looking at X-rays from cosmic objects. X-rays come from especially energetic objects, and so they're a way to highlight, in our view of the sky, the object especially exciting. It started off with sounding rockets being sent, so they got a few minutes observation before they came crashing down again. But then the first satellites were launched in about 1970 to study the sky in X-rays, and they found the first evidence for black holes orbiting stars. I had a lot of contact with Ken Pounds, who was then a young lecturer at Leicester, who managed, through his energy and initiative, to make Leicester a major international centre for space science, and his group were important in X-ray astronomy. That was something that I was very interested in.
So at that time, were black holes something that people had thought about, but they hadn't got any demonstrable evidence for? They were a theory, but you actually have now seen over your career them manifest for real.
That's right. I mean, the theory was worked out. Some bits were done very early on. Some bits, incidentally, were done by Oppenheimer in 1939, before he was otherwise distracted. And a lot was done in the 1960s under the inspiration of Roger Penrose, bringing new mathematics into it. But on the observational side, I think when these objects appeared in surveys of the sky, which couldn't be ordinary stars, they were too bright, varying too rapidly, etc., I think from the mid to late 60s, everyone speculated that they could be black holes, but the evidence was rather indirect, and some of my early work was in trying to work out how gas swirling down into a black hole could produce X-rays and things varying rapidly, and this could explain some of these things. But it wasn't until the late 70s, 10 to 15 years later, that there was a general agreement that what was causing the big energy output from the centre to some galaxies was flow around a black hole. It gradually emerged.
While I've got one of the foremost experts on this sitting next to me, can you explain to me the differences between the massive black holes we see at the centres of galaxies and the littler ones we see doing collisions that we can pick up with our gravitational wave detectors and so on? What's the difference between them apart from size, and what's their origin?
One feature of black holes is that they are scalable. In fact, a black hole of a few times the mass of the Sun and a black hole a few million times the mass of the Sun, like the ones in some galaxies, they are exactly the same in their properties. It's just a simple scaling factor. And they are the same, and they form in different ways, of course. Some stars end their lives collapsing and leaving black holes behind, and those are the ones which we see in binary star systems in our galaxy, and incidentally those are the ones that give rise to the gravitational waves that have been detected. Two black holes weighing about between 10 and 50 times as much as the Sun crashing together. But there is a separate category of supermassive black holes which form somehow by an agglomeration of mass in the centre of a galaxy. It's still debated whether the mass accumulates by just gas falling in, or do lots of stars collide and fall together. All those things play some part. All we know is that there are, in the sense of galaxies, black holes where the biggest ones are several billion times the mass of the Sun. In our galactic centre, there's one which is about 4 million times the mass of the Sun. That's small by the standards of these massive black holes, but of course much bigger than any star. And in fact, Don Lyndon Bell, who was my senior colleague in Cambridge, and I wrote a paper back in 1971, first arguing that there could be a massive black hole in our galactic centre, and that, of course, has been firmed up gradually over the years.
What you've just demonstrated incredibly eloquently is the other thing that you've become incredibly well known for, which is popularisation and explaining very complicated aspects of science. Was that something that just came naturally, or did you see there was a need, and so you thought someone has to step up and has got to fill this space?
Well, of course, astronomy is a subject which does lend itself to popularisation. There's a natural interest. I mean, young kids are fascinated most of all by, I guess, space and dinosaurs, both blazingly irrelevant but both fascinating. And I think if you look back over the history, many of the leading astronomers have also been popularisers. I think of Eddington and Hoyle. And there's a huge market now, and Patrick Moore and all the rest of it have amplified that market. I'm not such a fluent writer as some of them, but I would get less satisfaction if I could only talk about my work to a few fellow specialists. I think it's an extra gratification that one does get a response to these ideas and these discoveries from a wider public. But of course, if you are sort of sitting next to someone on a plane or something like that, if you don't want to talk at all, you say you're a mathematician. That'll shut them up. But if you do want to talk, you say you're an astronomer. But then the first question they ask is probably, are we alone? Life in the universe, as I'm sure you find in your experience of popularising science, and understandably so. And to jump forward a bit, that's a subject which has become a serious branch of astronomy with the James Webb Telescope, and even more, I think, with the world's biggest ground-based telescope, which is being built in Chile, called the Extremely Large Telescope. And this will have a major mirror, which is 39 metres across. Not one big sheet of glass, but a mosaic of about 800 bits of glass. And this will detect enough light to actually be able to get a spectrum of some of these planets, much more area than the James Webb, although James Webb can go into the infrared and see cooler things than you can see from the ground.
Did you not have a hand in making sure James Webb happened? I read somewhere.
Well, only very indirectly. I was, at the time it was being discussed, chairman of the European Space Agency's Science Advisory Committee, and there was an issue of whether Europe would have some fraction of it, about 10%. And so I was involved in those discussions. I think the European Space Agency has overall been a very successful organisation. I mean, it's far less visible in the public eye than NASA. But if you look at the actual straight science it does, it's comparable because it has some big projects. The best project, you look at the background cosmic radiation called Planck. There's now a probe going to study the moons of Jupiter. And an amazing project called Gaia to study the stars in the Milky Way has studied 2 billion stars. Of course, that just indicates how in our subject we have changed from being a subject where we're starved of data to one where you need computers to analyse all the data. And incidentally, in the kind of work I do, I used to develop sort of simple ideas about gas falling into galaxies and black holes and all that, and just hand-waving in simple arguments. But now computer simulations, the kind of simulations that they use in the weather forecasting, etc., they can do detailed modelling of how gas falls into protogalaxies and how gas swirls down into a black hole, etc. And one is doing, as it were, experiments in the virtual world of a computer, because in astronomy you can't do real experiments, you can't really crash stars and galaxies together, but in the virtual world you can, and then you can make different assumptions and then see if you see something up in the sky which resembles the output from your computer. And that's how we've made huge progress in the last 20 years.
I read a very interesting quote from yourself, which it was one of those things that makes you really think. And you said, some of the aha insights that scientists strive for may have to wait for the emergence of post-human intellects. Are you getting at this sort of thing where we have to invent something that can think more deep thoughts than we can, like AI-type approaches that will get at problems that are currently intractable for a human brain.
What I was referring to in that context was that perhaps if you want to have the kind of theory which will be needed to understand the very beginning of the universe and what happens deep inside black holes, where we have to have a unified theory that links together gravity, the force that governs a large-scale universe, with the quantum world, a so-called grand unified theory, then it could be that the mathematics is so hard we can't grasp it. You may know that there's a theory called string theory, which is being developed by people who want to understand the particles the world is made of and link gravity together. And this is a theory which you can write it down, and there are lots of variants of it, but it involves not just 3 dimensions of space, but about 10 dimensions of space. So it's very, very complicated. And I think the quote you read out is something where I've said that it could be that a machine can work through the very elaborate mathematics and geometry involved among these theories, and after churning away, it may come up with the right value for the strength of gravity, the mass of the electron, or something like that. And if it does, then we know that theory has something in it, and we can confidently then apply that theory to other problems like the early universe, etc. But we may not really have an insight. So that's what I meant, that what we like is to have a theory which, once we've got the idea, we say, aha, why didn't I think of that before? And that's true in many cases. Something in retrospect seems quite obvious. So there may be this class of theories for which we never have the insight in any human brain. But that leads to another point, which I often emphasize in general talks, which is that we shouldn't think of our brains as the culmination, because everyone accepts that we're the outcome of nearly 4 billion years of biological evolution, from the first life to the wonderful biosphere here on Earth, of which we're a part. But many people who accept all that somehow tend to think that we are the whole culmination, the top of the tree. But no astronomer can believe that, because we know that the sun's been around for 4.5 billion years, but it's got about 6 billion more before it flares up and dies. And the universe can go on much longer still. We could be nearer the beginning than the end of the emergence of complexity in the universe. But of course, what will post-human evolution be like? The key question then is, have we got nearly to the limits of what flesh and blood brains can do? So will it be that future evolution will be dominated by electronic entities of some kind, which will be our sort of progeny, our descendants, and then that evolution will be not Darwinian. It'll be what I like to call secular intelligent design, machines designing better machines. That's a possibility, and then those machines would have far greater capabilities. Whether they would have consciousness and comprehension, we don't know, and that's a very important question. That's a philosophical question. I think we are perhaps, as humans, at a pivotal transition stage in evolution when there be a change from Darwinian selection to something new, and these electronic entities will have no particular reason to stay on a planet. They may prefer zero gravity where they can build big structures, etc., and so they will go off out there. And this leads to another question, which is, will we detect evidence for alien intelligence? And of course there are searches for this. In fact, I chair a committee bankrolled by a Russian-American billionaire called Yuri Milner, who's putting money into an improved search for telescopes to detect any artificial-looking transmission. I think this is very worthwhile, although the chances of success are small. I think if we ask what are we expecting to find, I think we might not find anything that resembles us. Intelligence may be something which is entirely electronic and therefore not expansionist, etc., and not familiar at all. There's an argument called the Fermi paradox, which is often used to say that if there were lots of aliens, why wouldn't they have come here already? Because there were some stars older than the sun which would have had planets with a head start in evolution over ours. I think if one argues that post-human and more technically advanced entities are not flesh and blood, they may not have sort of instincts flesh and blood creatures do, and therefore not be expansionist. So the fact that we haven't seen evidence for these entities doesn't mean they're not there.
Is it also not the case that the problems one would have to surmount in physics and technology and engineering to get here would mean that presumably these people would know far more than they could possibly learn by coming here? So is it worth their while?
Well, indeed, I think that's true. The only counter-argument to that is that if they're electronic, they're probably near immortal, and therefore they would not be deterred by a voyage of maybe 10,000 years. And of course, they may have these very long timescales. But I think you're quite right that if they're out there, they may know that we're here and they'll be watching us, or they may not be interested.
But closer to home,
Yes.
one of the other things that you point out is that you're hoping that by mid-century we will have really thoroughly surveyed our own solar system, but not as us humans, but doing this as flotillas of robotic explorers. Because I think you were one of the first people who made me think about, well, why have we devoted so much time, effort and energy to preserving the frailty of human existence in space, when in fact a machine doesn't have all those constraints?
Yes. Whereas true, robots have advanced hugely in the last few decades. I think that advance weakens the practical case for sending humans into space, because humans are fragile. To send a robot to Mars isn't a hugely big deal. It just hibernates on the way, etc. Whereas to send a person to Mars involves 6 months of food and all that, and the provisions to bring them back. So it's hugely expensive. The cost gap is enormous. And it's true that robots can't do what a human would do. There are some robotic vehicles crawling around on Mars. There's one called Curiosity that got there about 12 years ago, and that trundled very slowly across a big Martian crater because it had to report back to base if it wanted to change direction when it encountered an obstacle. The later one, called Perseverance, has enough intelligence to work its way around obstacles, but it can't do geology. But within 20 years, one can imagine that there can be a probe which can study what's a good place to dig and actually get the samples itself.
Can we talk politics for a minute? Because one of the things that you did in the last decade or so, you joined the House of Lords. Robert Winston mentioned to us that you'd talked to him before you did that, when we spoke to him. Why did you decide to go down that road? Had you always been quite politically active? Did you have a particular plan in mind with doing that?
Well, I'd always been fairly politically active. It was an opportunity when I had the chance to join the Lords as a crossbencher.
Are there many scientists in your number in the Lords, though? We've seen so much of this in the last few years, haven't we, where we're being told that we're following the science and so on. But in fact, when you look for the ability to guide a lot of this, there are not many of them.
That's right, but as I say, one has to distinguish the science itself and the consequences and how its consequences are implemented. And of course, there are lots of issues like embryo research and things like that, and of course dealing with pandemics when there's a choice of policy options. And although the politicians should have the best scientific advice during the pandemics and all that, then the choice involves economics, politics and ethics. And in those arenas, the scientists have no special expertise. So I think there's a transition in any public debate between getting the science as right as we can, and then when we know the science, that still opens up a range of options. It did in the case of the pandemic, are masks a good idea? Should we shut down the schools and all that? Those were more general issues than just science. And the same is true in defence research and things of that kind. So I think we need to ensure that the best science is taken advantage of, and also that the public and politicians in particular are aware that much of science is provisional. Some science is pretty well understood, and gets better understood. In the early days of the pandemic, it really wasn't clear exactly what was the right thing to do, but the scientists acquit themselves well in developing vaccines quickly and all that. And that's true. I mean, in climate science, 20 or 30 years ago, it was genuinely very uncertain, whereas now the basic outlines are pretty certain, but that leaves open the question of the trade-off between adaptation and mitigation and all that. So more and more of the issues of politics have a scientific dimension. And that's why we do need more scientists. I'm not denying that in politics. But we also need better education, because one of the problems is that it's all too easy for someone to be bamboozled by bad statistics and things like that. And that's why we should be grateful for people like our friend David Spiegelhalter, who did a great deal to explain very clearly what one can believe and false positives and all that sort of technicalities in statistics. And so we need people like that. And I think it's sad if the public doesn't understand the basic aspect of nature of, why the seasons occur and life and all that. But I think scientists shouldn't bemoan ignorance among the public of their subject too much, because frankly the public is ignorant about too many things. It's sad if the public doesn't really understand Darwinian evolution and basic features of the natural world, but it's just as sad if they don't know their nation's history and can't find Gaza or South Korea on a map, and many people can't do those things. So I think education is something where we do need to focus and aim for higher standards.
You wrote 2 books in the last year or so.
Yes.
What are your plans for the year ahead?
Well, I'm writing 2 more at the moment. One is it's on the big unknowns in science, and I've got to try and humanise this by putting in short sketches of the interesting and successful scientists who I've been privileged to know, and another short book with a collaborator called Alan Lightman on what's it like to be a scientist, a more subjective one.
I look forward to reading them and then coming and interviewing you about them when I've been through them.
Right. Well, thank you very much.
Thanks very much to Martin Rees. Well, that's all we have time for this week, but do join us again next time for the final instalment in this season of Titans of Science, when we'll hear from the leading authority on neuropsychological genetics, Professor Julie Williams. I hope you can join us then. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.